So yesterday, um, while discussing asymptotes, we found out how to find vertical asymptotes, horizontal asymptotes, and inclined asymptotes. So now today there is another method. Sometimes it is not so easy to write the curve as an explicit function of x. Like here, y is equal to f of x. So many times it is very difficult to write the curve as an explicit function of x. So in such cases, how do we find the asymptote? It's a simple method, but a concept involved behind it. So yeah. So for vertical asymptotes, at a, if the function value goes to infinity, either plus or minus, when we approach a either from the right or the left, we get x equal to a as the vertical asymptote. Like for tan x graph, which is a well-known graph for us, at x equal to pi by 2, 3 pi by 2, minus pi by 2, these are all vertical asymptotes. For horizontal asymptotes, as x goes to infinity, the function value should approach a constant, constant b, whether x approaches either plus infinity or minus infinity, then that is the horizontal asymptote. For inclined asymptote, we discussed yesterday that f dash x upon x, as x approaches plus infinity, will give us the slope of the asymptotic line, and f of x minus that k1x as x tends to infinity will give us the constant. So yesterday I explained this. So if this happens, then y equal to k1x plus b1 is an inclined right asymptote. And if the same thing we get for x tending to minus infinity, that is called as the inclined left asymptote. Now, alternative method for finding asymptotes, this will work for horizontal and inclined asymptotes, but it cannot work for vertical asymptotes because the slope will be infinity. So that you have to do by inspection only. However, look at this. So first point, the curve of degree n cannot have more than n asymptotes, real or imaginary. So maximum number of asymptotes is equal to the degree of the equation, degree of the curve. Now, so how to find? When we write the equation of the curve, equate the higher degree terms to 0 and then factorize. And if x minus m1x is a factor, then that correspondingly we'll get one asymptote y minus m1x is equal to c1 will be the corresponding asymptote. So when we were doing tangents at origin, we equated the least degree terms to 0. But when we have to find asymptotes, x approaching infinity, we have to go for the highest degree terms, equate them to 0. So if we get one of the factors, linear factors in x and y, so that factor equal to some constant will give us the asymptotic line. Now, how to find this constant? So in the equation, either once we have to find C1, M1 is already found because by the process of factorizing, we found out. So now either write y in terms of x and c1 like this, or x in terms of y and c1. So, and then substitute this expression back into the curve. So what happens is the highest degree term becomes 0, and the next highest degree term we have to take. So then what happens? The highest degree term, that coefficient we should equate to 0. When we equate that coefficient to 0, we will find C1. And once we find C1, we get the asymptote y minus m1x is equal to C1. So that will be the asymptote. This simple step. This works pretty much. We can get asymptotes by the previous methods for most of the curves. Sometimes we'll not be able to do for implicit definitions of curves. So that time this method can be used. And this method is again based on the concept that as x tends to infinity, the slope of the line approaches m1 and the function coincides with this line. So this is standard one. Now let us do some examples. It will make it very clear. The first one is simple. You can do it. I will start with the second curve. So let's find the asymptotes of this curve. So this is the first one. Let's find the asymptotes of y equal to 5x by x minus 3. So first step to do, we can see as first of all, by observation, we can understand that x can take any real value except 3, because y can take any real value, isn't it? It is not y square. That right hand side has to be positive. So right hand side can be positive or negative. So x can take any real values except for 3. So as x tends to 3 minus or x tends to 3 plus, okay, y is tending to y, which is same as f of x, is tending to infinity, either plus or minus, that we have to see. So in fact, if it's less than 3, this will be negative, so it will go to minus infinity or plus infinity respectively. So therefore x equal to 3 is a vertical asymptote. Very good. Very simple, straightforward. Now next, do we have a horizontal asymptote? That we have to check. Now, as x tends to infinity, plus or minus, let us see. So limit x tends to infinity, the function f of x by x minus 3 will be limit x tends to infinity, divide by x, 5 upon, divide numerator and denominator by x, we get this. So as x tends to infinity, 1 by x tends to 0. So it goes to 5. So we get, therefore, y equal to 5 is a horizontal asymptote. y equal to 5 is a horizontal asymptote. Okay. So we have two asymptotes, and degree of this equation, if you multiply x with y, you will get degree 2. So maximum two asymptotes. So let us plot the curve and see how it looks. Now, x equal to 3 and y equal to 5. So x equal to 3, let's say this is 3. So this line I'm putting as a dotted line, but this line is the asymptote. X equal to 3 and then y is equal to 5, slightly higher here. Just a second, please. Okay, sorry for the interruption. So now let me plot this curve. This is y equal to 5x upon x minus 3. 5x upon x minus 3. So y is equal to Now what I'll do, I'll multiply, I will subtract and add this 3. So I'll get, when I divide the first, I'll take x minus 3 as one factor. So that divides, I'll get 5 plus 15 upon x minus 3. So here we see as x tends to infinity, I'll get y going to 5. All right. And as x tends to minus infinity, again, y will go to 5. So that is not an issue. However, when x tends to 3 plus, it goes to plus infinity because there's plus infinity. And when x tends to 3 minus, it goes to minus infinity. So in fact, it is like this. The curve will be like this. Now, can anybody say what type of curve is this? What type of curve is this?
Sir, hyperbola.
Yes, this is an hyperbola. I'll give you a trick. In hyperbola, hyperbola has a form. L1 into L2 is equal to constant. Product of two lines is equal to constant. Will give us a hyperbola, okay, where L1 equal to 0 and L2 equal to 0 will be its asymptotes. Okay. So look at this equation now. So I will just rearrange the terms. Y minus 5 I'll bring to the left side is 15 upon x minus 3. So this will give us x minus 3 times y minus 5 is equal to 15. Okay, so this is now in the form of L1 into L2 is equal to constant. So the asymptotes will be x equal to 3, x equal to 3 and y equal to 5. So this is y equal to 5, this line, and this is x equal to 3. These are the asymptotes. And because the lines are perpendicular, this is a rectangular hyperbola. The asymptotes are perpendicular. It's a rectangular hyperbola. In the next example that we'll see, the asymptotes will not be perpendicular. So let us look at the next example. So this is the way the curve looks, and this is the asymptotes. Here question was just to find the asymptotes, not to trace the curve, but I have drawn the curve. Next, let us look at this one. So example 2. So find the asymptotes of this curve. Very clearly, you can tell one asymptote what it is just by observation.
X minus x is equal to 1.
X equal to 1. Good. Good. So as x tends to 1, y goes to infinity. It can go to minus or plus infinity depending on left or right. So therefore, x equal to 1 is an asymptote. Now, let us try as x tends to infinity. So limit x tends to infinity of y or f of x. Let's say what happens to the function. This one x tends to infinity, we divide by x, you will get 3 upon 1 minus 1 by x. This we can't do anything. So we get 3 plus infinity. So it is going to infinity, it is not going to a constant. Therefore, there is no horizontal tangent, no horizontal asymptote. Next, now look at the inclined asymptote. For inclined asymptote, what do we have to do? Limit x tends to infinity, f of x upon x. So limit x tends to infinity, this expression divided by x, we will straight away get 3 upon x minus 1 plus 3. We have divided this expression by x. Now this will go to 0 plus 3. So slope of the line is 3. Even if you make x tends to minus infinity, again it will tend to the, you make x tends to minus infinity, again this will go to 0 and the limit value will be plus 3. So you will get only one asymptote. So this is the slope. So therefore y is equal to 3x plus c is an asymptote. Now this is an asymptote. Now how to find c? Okay, to find c, we have to do c is limit x tends to infinity, f of x minus kx. So f of x minus 3x in this case, f of x is 3x by x minus 1 plus 3x minus kx. Kx is 3x. So this cancels. And then we have limit x tends to infinity. You divide by x, you get 3 upon 1 minus 1 upon x. We get the value as 3. Okay. So therefore, the asymptote is the inclined asymptote y equal to 3x plus 3 is an inclined asymptote. Again, how many, what is the degree of this curve? 2. So only 2 asymptotes. So we have got x equal to 1 as one asymptote. This is the first asymptote. And this one is the second asymptote. So now let us plot how the curve looks like. X equal to 1. This is x equal to 1 and y is equal to 3x plus 3. So 1, 2, 3. And the slope is large slope. Okay. Now they would intersect at some point, y equal to 6, x equal to 1, y equal to 6. Now these are the asymptotes. Now where does the curve lie? Now let us see how can I make this equation into L1, L2 equal to constant. So I get y minus 3x is equal to 3x by x minus 1. So my line is y minus 3x minus 3. So I will subtract 3 both sides. So what do I get? 3x cancels. I'll get 3 upon x minus 1. So I get x minus 1 into y minus 3x minus 3 equal to constant. So we can see now either the curves lie in this region or this region. So you should take one of the points here and check for what value of x you will get the value of y. So here, of course, this is L1, L2 is equal to 3. Sometimes we can find out by the sign of the constant. If the constant is negative, it will lie in one quadrant. It is constant and positive, it will lie in the other two quadrants. So now let us check. See, this is x equal to 1. When x is equal to 2, where does the point lie? Substitute x equal to 2. We get y value as 6 plus 6, 12. So it will be here. So the curve will lie in this region. So, and it is a hyperbola. So hyperbolic curve, something like this. And then another branch of the hyperbola will exist in the opposite side. Okay, this will be the equation of the, this will be the graph of this curve. This is hyperbola. So this is how we find the asymptotes and the curve. So by seeing the equation, we can predict which kind of curve it is, and you can do these other two problems. There's also again hyperbolic type of problem. Now let us look at this question. Sorry. So this is an important question. This curve yesterday we plotted. All right, it was this particular curve. It has a name. It is called folium of Descartes. Of course, we don't have to worry about this terminology, but yesterday we saw the plot of it. It has two tangents at origin, x equal to 0, y equal to 0. Now, how will be the asymptote of this curve? So now we cannot explicitly write y in terms of x. Like we could not write y purely as a function of x. The function is implicitly defined. So now we cannot use these limit as x tends to some constant, what will be the function going to? Limit on f of x. F of x you cannot clearly write in terms of x. So we will have to use this alternative method. What is that? Equate the higher degree terms to 0 and then factorize. If one factor is y minus mx, y minus m1x, then the corresponding asymptote is y minus m1x is equal to c1. So let's do that. So now this equation is equation of the curve is this. Now this is degree 2 term and these two are degree 3 terms. So third degree, it's a third degree equation. Now equate the highest degree terms to 0. Equate the highest degree terms to 0. So we get x cube plus y cube equal to 0, which implies x. Now we have to factorize. We get x plus y into x square minus xy plus y square as the two factors. Now we get one linear factor, one non-linear irreducible factor. We cannot reduce this. We can try, it cannot be reduced. This discriminant for this quadratic will be negative, so it cannot be factorized. So it doesn't have real factors. Now you have one linear factor here. So therefore, x plus y equal to k or equal to c is an asymptote of this curve. Directly, we can conclude this. Now, how to find c? Substitute y equal to c minus x in the equation of the curve. So in the equation of the curve y equal to c minus x, we get x cube plus c minus x whole cube minus 3a into x into c minus x equal to 0. Now expand and simplify. X cube plus c cube minus 3c square x plus 3c x square minus x cube minus 3a cx plus 3a x square equal to 0. Now what happens? X cube and x cube cancels. So we are left with 3c x square and 3a x square. So 3 times c plus a times x square minus 3 times c square plus ac x plus c cube equal to 0. Now equate the coefficient of highest degree to 0. So what do we get? C plus a equal to 0, which implies c equal to minus a. Therefore, the asymptote is x plus y equal to c, right? So x plus y equal to minus a, which is x plus y plus a equal to 0. Okay, let's look at the curve that we plotted yesterday. The volume of Descartes. Something. It's taking time to load. Yeah, it's over. So let us plot, put a equal to 1 and plot x cube plus y cube is equal to 3xy. This is the volume of Descartes. Now, the next line, I will plot x plus y plus a. A was 1, right? So the next equation, x plus y plus 1 equal to 0. We can see the equation of this line. So see this line is asymptotic to this curve. You go more and more closer, you can see this curve is getting closer and closer to this line, but it will never touch. So what we found, the asymptote is right. Now, suppose I make a is equal to 2. So I get x cube plus y cube equal to 6xy. So my asymptote should be x plus y plus a. So a should be 2. I do that. And there we see this is the asymptote. Okay. Yeah, there's the curve. This is the volume of Descartes. So this is how we find asymptotes. So this much is sufficient for us. There are much deeper details, and there are some more difficult curves for which you can find asymptotes, but this is the principle. If you just practice this much, that's sufficient. Now, moving forward with our discussion on curve tracing. Next, in tracing a curve, we should understand tangents, normals, which are the stationary points meaning which are the points where the derivative is 0 and where the function is discontinuous. What is the point of maximum, point of minimum, the maximum, minimum value, so on. So to find the tangent normals at any point of the curve, to find the monotonicity of the curve, and to find the points of maxima and minima of the curve, the concepts of differential calculus have to be used as studies during the course in differential calculus. So this we have already done it. So that is required for us when tracing a curve accurately. And then finally, we have what we have already discussed earlier is the concept of, the curvature, whether it is concave or convex. So it will be concave up or simply concave if the second derivative of the curve of f of x is positive, and it will be convex if the second derivative is negative. And if the second derivative is 0, the second derivative is 0, and the second derivative changes sign when passing through that point where the second derivative is 0, then that point a comma f of a is called as the point of inflection. So this we have discussed earlier in the earlier class. So example 0 comma 0 is the point of inflection of y equal to x cube. So basically the curvature changes from concave to convex or vice versa. So at the point of inflection. Now, so for some curves, the second derivative may be 0, but the third derivative or the second derivative does not change sign, then it will not be a point of inflection. And sometimes this second derivative is undefined, it goes to infinity. However, still point of inflection exists where f double dash x changes sign as we move across x equal to 0. You can try this out. So that's why in the strict definition, we say if at x equal to a, f double dash x is 0 or undefined, or it is undefined, it does not exist. That means f double dash goes to infinity. Then point of inflection does not exist. So, sorry, point of inflection still exists as long as the second derivative changes sign. So let's look at such an equation. So this is cube root x. Y is equal to cube root x. If we expand and see, the curve, we will see that so we'll see that the second derivative goes to infinity for this one, y equal to cube root x. All right, but the second derivative changes sign. Here, second derivative will be negative. Here, the second derivative will be positive. You can check that. Okay, I'll leave that exercise to you. So, point of inflection is a point where the curve crosses over its own tangent. So these are some basic definitions on basic concepts in tracing out a curve. These are useful in tracing a curve. It is not that all the concepts are simultaneously used in one curve. In some curves, more number of concepts may have to be used. In some curves, less number of concepts may have to be used. But these concepts help us to have a grip of how the graphs of functions change. So with this, we finish the curve tracing. All right. So these notes I've sent to you by in our group yesterday. You can go through them. Next is I should change this title. So curve tracing. Now, next we will add rectification, application of integrals. Okay. Now, let's go back. So, application of integrals. We have these three applications. So now we are going to discuss the first one of the three, the length of plane curves, or what we call as rectification. This is what we'll discuss here. So how do we find the length. So let us do this. I will first explain the concept like this. All right. So if S represents the length, arc length function of the curve y equal to f of x, then the following relationships can be shown to be shown to hold true. So let us see this. This is very important. Now let us say we have a function. Now this is a curve. This is a curve. Now I want to find out the length of the curve between 2 points. Now it's not a straight line. Okay. I want to find the arc length, the curved length along the curve. I want to find the length. How do I do? Now just consider a very small portion. This is also large, but we are enlarging it. Okay, we are enlarging this portion. Now let this length be delta x, and correspondingly this length is delta y. Okay, this is delta x and this is delta y, and this arc length, let it be s. Now as delta x tends to 0, delta y will also tend to 0. Let's say this is point P, this point Q. The point P and Q come closer and closer. Then what happens? It is more or less like a straight line. When it is so infinitesimally small, P and Q distance are infinitesimally small. So we can replace this delta x by dx, a differential increment, and dy by delta y by dy, and this length by ds. Clear? So now what do we get? So we are now approximating it, because as these delta tend to 0, Pythagoras theorem holds ds square is equal to dx square plus dy square. All right, as delta tends to 0. So this is the concept. So the most critical expression here is this one. ds square is equal to dx square plus dy square. If you remember this, from here you can derive all the others. So you understood what we have done. We have taken a very differential element, increment in x and increment in y. As you know, the increments tend to 0, we can approximate this by a right angle triangle and use Pythagoras theorem and write ds square as dx square plus dy square, and it works. So from here, because ds square is equal to dx square plus dy square. This is what we find. So from here, you divide by x square, dx square. So you'll get 1 plus dy by dx, the whole square. This is whole square. ds by dx whole square is this. So we get ds by dx is under root of 1 plus dy by dx the whole square. This implies ds is equal to under root of 1 plus dy by dx the whole square times dx. So that is what we get. So ds can be written as under root of 1 plus dy by dx whole square times dx, or ds is under root of 1 plus, if it is y is an explicit function, so f dash x whole square dx. Similarly, from the same one, you can write in terms of y. So sometimes it is easier integrating with respect to y. So similarly, we will, if we divide by dy square at that point, so we will get 1 plus dx by dy the whole square times dy. Okay. So this is if the given expressions is in Cartesian form. Now, next, sometimes if equation of the curve is in parametric form. Parametric form. X is equal to x of t, some parameter, and y is equal to y of t. Then simple. Dx will be dx upon dt times dt, and dy is equal to dy by dt times dt. Okay. So from here, so dy by dt, dy by dx is dy upon dt by dx upon dt. Okay. Next, beyond this, now, so what happens? So ds, which is under root of 1 plus dy by dx the whole square times dx, will become in the parametric form 1 plus this term, okay, dy by dt by dx by dt the whole square. We can find that out. And this dx will be dx by dt times dt. So when it's a parametric differentiation. So if this curve is in Cartesian form, then directly these are the results for Cartesian form. Okay, curve in Cartesian form. So equation of curve in Cartesian form, equation of curve in parametric form. Now, if the equation of the curve is in polar form, how do we do it? What is polar form? Equation of the curve is in terms of r and theta. What are polar coordinates? See, in Cartesian coordinates, we have two axes, x and y, and any point P is written in the form of x and y coordinate. So the reference point is the origin. This is the x coordinate. The distance to reach this point P, we have to move x distance along the x-axis and then a distance of y units along the y-axis. So we get this point P, this one. Now in polar coordinates, we don't have origin. We call this as pole. This is the pole. And we have one horizontal line called as the initial line. Okay, we can try to coincide the initial line with the x-axis. This is the initial line. Now, that's it. With one pole and the initial line, we can define any point in the plane. How? So let's say the similar point P we take here. The distance of this point P from O is called as R. The distance from O to P is called R, and this ray OP, if it makes an angle of theta in anticlockwise direction with respect to the initial line, so this angle is theta. So P is defined in terms of R and theta. These are polar coordinates. Many times solving problems in polar coordinates becomes very easy. This is Cartesian coordinates. So these are something that you know. I'm just reviewing in a manner that you can easily remember. So now what is the relationship between the polar coordinates and the Cartesian coordinates? So if you drop a perpendicular from P onto the initial line, now, and you take O as the origin of the Cartesian coordinates, initial line as the x-axis, then just a second. Sorry, I have some urgent things that is going on. That's why there's distraction. Um, so, so where were we? We were discussing the relationship between polar coordinates and Cartesian coordinates. So when we drop a perpendicular from P to the initial line, and let's say this coincides with the x-axis, this will be the y-axis, then this will be x and this will be y in terms of Cartesian coordinates. So when we equate relation between Cartesian and polar coordinates, relationship between Cartesian and polar coordinates. So what we get is this symbol. X, you can see, is r cos theta, and y is equal to r sin theta. This is the relationship between Cartesian coordinates and the polar coordinates for the same point P. So now I want to have a derivative like this, right? ds um, ds square is dx square plus dy square. This is the differential equation that I have. So what will be dx here? Please note that here for defining a point, r varies and also theta varies. For any point, theta can vary from 0 to 360. R can take values from 0 to infinity. It will cover the entire space. So r is changing and theta is changing. So we'll have to apply UV rule for this. So dx will be derivative of the first variable, keeping the second variable as constant. Then keeping the second variable as first variable as constant, differentiating the second, cos theta, derivative is minus sine theta into d theta. So this is the differential. Dx is this. What is dy? Similarly, dr sine theta, then r, derivative of sine theta is cos theta d theta. So applying UV rule. Okay. Now, what will be squaring and adding? Squaring and adding the above two, we'll get dx square plus dy square will be what? Dr cos theta minus r sin theta d theta square plus dr sin theta plus r cos theta d theta square. So when we square and add, you will get dr square times cos square theta plus sin square theta. So you will get dr square. Then minus 2r cos theta sin theta dr d theta. Here you will get plus 2r cos theta sin theta dr d theta. They will get cancelled. And the last term, r square d theta square sin square theta, r square d theta square cos square theta. So r square d theta square times sin square theta plus cos square theta, that is 1. So you will get r square d theta square. Very, very important result. So if you remember this, ds square, which is nothing but dx square plus dy square in Cartesian coordinates, but in polar coordinates, it changes to dr square plus r square d theta square. This, if you remember, you will not make any mistake in conversion. That's it. So now once we know this one, that ds square is a dr square plus r square d theta square. Okay. Now, if you divide by dr square, ds square by dr square is equal to 1 plus r square d theta square by dr square. All right. So which implies ds will be under root of 1 plus r square d theta by dr whole square times dr. Okay, this is one expression. Now, the same thing, if we divide by theta, ds square by d theta square is equal to dr square by d theta square plus r square, which implies ds is under root of r square plus dr by d theta whole square d theta. Got it? The conversion, how we did? It all hinges here. So let's go back here. So these are the two things which I derived and shown. So for this, the basis is this one. ds square is dr square plus r square d theta square. Okay. All right. So based on this, based on these two critical results, we can write the differentials in this form. Okay, that's what I've, and these give you the formula for finding the lengths of the plane curves in a very simple manner. From here, it is very straightforward. Once you understand this part, things very, very straightforward. So based on the above, relations, the length of the arc of a curve is calculated as follows. Very simple. So length of the arc of a curve y equal to f of x between 2 points on the curve whose abscissa are x equal to a and x equal to b. So we are integrating with respect to x. So our ds should be in terms of dx. So we choose the first result. Although there are two, either you can choose with respect to x or with respect to y. Because we have to integrate from x equal to a to x equal to b, we will choose this one with dx. So under root of 1 plus dy by dx the whole square times dx, integrating it from a to b. So ds was this. ds was under root of 1 plus dy by dx the whole square times dx. So length of the curve we want from between point A and point B. So integrating, you will get this point x equal to A to x equal to B. That's what we did. So that's how when you apply the integral, you will find the length of this curve. Now, if we have to integrate with respect to points, say y equal to c and y equal to d, then the ds formula we write in terms of y under root of 1 plus dx by dy the whole square times dy, integrating it from c to d. Okay. Next, if it is parametric, so very simple. Here, the parametric form ds square is dx square plus dy square. So ds square by dt square is dx upon dt the whole square plus dy upon dt the whole square. Okay. So ds is under root of dx upon dt the whole square plus dy by dt upon dy upon dt the whole square times dt. And then we can integrate it. To find s, we can integrate this from the given values of t equal to alpha to beta here. Now, so this was in parametric form if the curve is defined parametrically. Now, if the curve is defined as in the form of polar coordinates, r equal to f of theta, and we want to integrate with respect to theta. We will do problems on this. Sometimes it is very, very simple. The problem becomes extremely simple by integrating it using the polar form. Then if it with respect to theta, then our ds should be in terms of d theta. So this expression we will use. ds is equal to under root of r square plus dr upon d theta the whole square times d theta. So that's what we are writing here, and integrating it from limits theta 1 to theta 2. And if we can, if this derivative becomes easier, right? Writing theta in terms of r and d theta by dr is a simpler function. And if we have to integrate with respect to r1 from r1 to r2, then we use this expression. Okay. So that's how we find the lengths of the curves, lengths of plane curves. So with this, we will do problems in the next class. If possible, I may take an extra session during this week, maybe for 1 hour, not much. Maybe on a Wednesday or Thursday, if it is feasible for you. I'll put a time, and if it is feasible for you, you please respond to me. Then we can take up, and I'll cover the problems on rectifications and areas under curves. These are the two areas bounded between two curves and so on. And then we'll have to move to volumes and surface areas of solids of revolution. So, but there'll be a number of problems to discuss, and these are some very important areas. Some of the problems, both in polar coordinates also, questions have been asked in the past, and in Cartesian coordinates. So